Hi, and welcome to my series on production grade systems development. My name is Dave Oram and I'll be your guide today as we cover our episode that covers microservice development. If you want to follow along on your browser, go to github.com/davidoram/beaker. Otherwise you can just watch the video along as I go through the code. In previous episodes, we've covered all the layers that we need to do to get to this point. So we talked about our development environment using code spaces. Inside that environment, we're running Postgres as our database. That's where we store all our data from our microservice. Then we went up a layer and talked about how our Go application would access the Postgres database using tools like the PGX driver and SQL C to generate the boilerplate code that actually accesses database queries and results. Up from that, we talked about how and why we adopted JSON as our data interchange format, and then we use JSON schema to perform all of the validation tasks across that JSON. Again, moving from JSON to the application layer, we describe how we use the standard library Go marshalling, unmarshalling techniques to move data from JSON into Go structures. Finally, we touched on telemetry and we use that to record our system behavior at runtime. So in today's video, with all of that in place, we're going to draw those pieces together and actually write our microservice. Nets provides a framework for building microservices. So if you open this page, I'll put the link in. It tells you how to build their microservices using that, some of the concepts and how that works. So let's cover what a service is. Service is a group of related functions. So in our case, those functions center around the concept of inventory. Inside the service, there's a bunch of different endpoints. Those are the different API entry points that a user could call into to perform different operations on our inventory. So in our case, those operations are things like add inventory, remove inventory, and query to see what the current inventory state is. Another important part of microservice delivery is how callers will discover the microservices. So they need a way to sort of query the system, or some way to determine what the endpoints are and how they call them. So those things are covered off in this document here. So from a Nets perspective, an endpoint is a subject. You can group endpoints together, and there are some service operations that provide that sort of discoverability side of things. You can ping the system and ask for all the services, and you get a bunch of metadata back which describe them all. So that's used by the Nets command line tool to query our Nets server. You can list all the services that we've registered and then start calling them. So we understand that Nets is a messaging system, and it allows messages kind of to flow multiple ways between clients and servers, servers and clients. So how does that translate to a kind of the request reply model that we have with an API call? When you write a Nets microservice using their framework, there's a structure under the covers that allows the Nets messaging system to do a request reply. The way it works is the requester or the caller will call the endpoint for your service, but it also supplies inside it the Nets subject where it wants the response to be sent. So that would look something like _inbox and then a bunch of unique random characters. So I'll make a call into a service, it provides that subject for the reply, then the service will receive that request and it's responsible for sending the reply back into that inbox response channel. All of that detail is hidden from us when we use the service framework, but it's important to know because the first thing we've got to do is we've got to create our Nets user with all the permissions it needs to act as a microservice. Now, we mentioned this earlier when I had the episode talking about our developer environment setup. So now I'm just going to take you through those users and show you how they've been set up. So we're going to head over to synadia.com/cloud And if you haven't signed up yet, you can click on the Get Started button, this one here, but I'm just going to sign in. It's important to note, if you are signing up, that you sign up for the Synadia Cloud option. Okay, so the first thing, the first page you'll be presented to once you logged in is the systems. So you can connect NAT systems running locally, maybe running on some IoT devices, and you can connect them all together through this dashboard. But the system we're going to use is the NATS global system. That's the one that's hosted in Synadia. So we'll just click through straight into that. The next screen you'll be presented with shows accounts. Now, accounts in NATS and Synadia are a form of isolation. So if you're writing a software as a service, you might have every one of your tenants have a separate accounts. Accounts, when we create users, they're created inside accounts. So by default, those users have only got access to the resources that are created within the same account. So it's a really nice form of isolating data and access. So we're going to click through into our default account. Once that loads, it shows us an overview of the information inside that account. So up the top here, we're going to click on the Users tab, and I'll show you the users that we've set up and what they're for. The first user here, app, is the user that our microservice will use to connect to NATS. Now, you can see under Publish and Subscribe permission, there are no values there, which means it's completely free to do what it wants, kind of like a root permission. In a normal scenario, you'd want to use the principle of least access permission. So when we set up any permission for any user, give it the least access it needs to do its job and no more. That's just good security practice. So I've applied those principles to this user inside NATS, which is called caller. This is the NATS user that would give out to our API callers. And so you can see under the Publish and Subscribe permissions, it's got some limitations there. So we allow publish to the stock dot greater than. That's anything that starts with stock. It can publish to subjects under that wildcard. Then you can see it's allowed to publish to underscore inbox, and it's allowed to subscribe to underscore inbox. So that gives it the rights to create that temporary subject where when it makes an API call, it's going to get the response into, because that's part of its responsibilities. And the last one is the $SRV. This is a system, I guess this is the top level subject for system discoverability and informational topics. So we give it access to that so it can actually use the standard NATS tools to go and discover what our services are, get some metadata about them, figure out their documentation, that sort of thing. So our third and final user is called CLI, and that's just one I created so I can call anything I want from the command line. In our earlier video about code space setup, we covered how we would create environment variables for our code space that contain all the credentials for our NATS users. So I'll just show you a little bit, remind you a little bit about how that works. So you would go into the user, click on the Get Connected button, and then download the credentials using this button here, which gives you a file on your local machine. That's the file, the credentials file that you upload to the code space and you base64 encode. Then with that base64 encoded value, you're going to click over into GitHub, go to your code space user secrets, and you're going to create secrets like I have here with that base64 encoded value. So we've got the 3 NATS creds values for the app, the caller, and the CLI users. When your code space starts up, it takes the values from these environment variables, base64 decodes them and puts them in files. Then as part of that startup sequence, it uses the nats context add command and passes in those files. So what this does is, that means the nats command line tool now has access to these three contexts, so it can assume them very easily. You know, I want to run this command as, say, the app user, or this command as the CLI user, etc. So that's just a real nice, convenient way to get those secrets in there, have them ready to use. Okay, so we can see those contexts in use by typing the nats context ls command. And you can see there we have our three contexts. We can choose to, set our default context to 1. That's currently set to the CLI. You can see it's got the star at the end here. That tells us that's our default context. If we don't specify a context on the nats command line tool, it'll use that one there. Right, let's start by using a command that lists the services that are running. Nats service ls. Okay, so we haven't run anything inside our code space. Our Beaker service isn't running yet, so it says there are no services started. So what we're going to do is we're going to open another terminal in the background. Let's do that, and let's run our make run command. So this is going to wait for Postgres to be ready, check all our code, compile it, and now run it at the end. And if you see something like info Beaker is running, that's the sign that it's run up. So let's run our nats service ls again, and there we can see it's recorded that the stock service has been registered with nats, so it can use that discovery mechanism to find out what it's called. So let's flip over to nats to see what's happened on that side of things. Let's go to the connections tab. When we refresh the page, we can see that the Beaker connection has been made. That represents our API service connecting into nats. We can click on any connection. You can see on the right hand side we get a bunch of details about that connection. The first section has got some connection details, IP addresses and ports it's connecting through, etc., when its last activity, and if the connection's online. The next section tells us about the account it's connected to, which is our default account, and the user that's actually made that connection. That's the app user. Further below we have the subscriptions that connection's made, and some statistics about how much data has been interchanged. So what we're going to do next, before we dive into the code, is we're just going to run some API calls to see what happens. So if you open the make file, we're going to look first at the test add command. So this runs the nats command line tool. It is going to explicitly set the context to be the caller. That's the nats user that we're going to give out to our API callers. It's going to issue a request that tells it that it's going to issue a request and get a reply using the standard framework conventions. And I'll come back to the translate command, but the next option is specifies the nats subject that the API request goes to. So in this case it's stock.add. And then inside these single quotes we've got the payload that's going to send. So we're adding stock to the product SKU coffee cup, and the quantity that we're adding is 10. Pretty straightforward stuff. Right, circling back to this -- translate option. So what this does is it gives us the option, after we've made the call and got the response, the nats command line tool will pass that response through this translation command. So that's kind of like a Unix standard way of piping one command, the output of one command into the input of another one. So we are going to translate our output, which is in JSON, through the JQ -- color output command. So that'll give us a nice colored, easy to read representation of our response. So let's run that now. Okay, we've got some results. We sent the request on stock.add. We received the response with a round trip time of 325 milliseconds. We have our trace parent header value. Reminder, that's how we access the trace for this request over through OpenTelemetry. And here's the response. So, okay, true. That's our signal that everything went okay. We'll get our product SKU, and now we've got the newly updated quantity. So just to prove that's working, we're going to add another 10 by running it straight away. And we see the quantity go from 18 plus another 10 equals 28. Great, that's working well. So let's just have a look at the make test remove. So very similar. It calls the stock remove endpoint and provides the product SKU, coffee cup, and the quantity. In this case, we're removing 7 at a time. So we started off at 28 and we ended up at 21. So that seems to be working correctly. The stock remove handler is one that we've added some special logic onto. When the stock level gets below our threshold of 10, it's going to publish a message to NATS. So let's have a look at that working now. If you scroll down a bit in the make file, you'll find the test-events target. That runs the NATS command, and it uses the sub option, which tells NATS we're going to supply a subject and we want you to subscribe to all the events that are published there. As per the previous command, we're going to translate all the output through JQ so we get a nice readable output. So let's run that over to the side here. Make test events. Okay, it's told us immediately it's subscribing on event.greater than, so any wildcard that starts with event. And now on the left hand side, I'm going to start removing, and we'll see what happens when we pass over the threshold of 10. So at 21, now we take off 7, we're at 14. Okay, we subtracted another 7, so now our quantity is down to 7. And you can see that NATS has published an event which we've been picked up in our other terminal. So our event subject is event.low_stock, and it's given us the product SKU and the new stock level of 7. So that's how that works. This is a really good way to design systems that interact in a loosely coupled way. So you could have a completely separate application that's just there listening for low stock events and then performing some action. Maybe it emails someone to reorder the stock. Maybe it interacts with with a supplier system directly and does their ordering for you. So you've got lots of options, but the key thing is because the systems are decoupled, our beacon microservice doesn't need to know how that system works. The only way they interact is through generation of the message. So that's kind of like a nice design principle. So now it's time for us to look at our microservice code. So we're going to start off with main.go, and this is something we've briefly touched on before, but let's go through it in a bit more detail. So you'll notice that this method calls a whole bunch of functions which are do something or exit. Now, all those things it's doing are things that are really required for the service to run. So if they don't run, there's some sort of problem starting them up, we're just going to exit the application straight away. So we don't want an application that's running that's kind of half connected to things. Maybe, it's got a database connection problem or a JSON schema compiler problem. We want all that stuff to be in place and working correctly before we start. So all of those functions, setting a time zone to UTC, we've talked about that, setting up our telemetry, creating our Postgres pool of connections. We're going to connect to NATS, and we're going to create our JSON schema compiler. Next, we're going to set up a signal handler what that does is it will trap like a Control-C signal or an exit signal from the operating system, and it will clean things up before we exit. Then we start the app or exit. Once all that's done, we can see it prints the message beaker is running, and then it waits for the context to be cancelled, for example by the signal handler, someone pressing Control-C, and then it prints shutting down the application. So let's dive into start app or exit. All this does is calls api.startNewApp, passing in the NATS connection, our database pool, and our JSON schema compiler. And if that doesn't work, it exits. So let's go into this. Start new app. As you can see, this function creates a new app structure, which we see is defined above. This serves as a holder to all of the resources that the app needs while it's running. So it's got a NATS connection, the database pool, a link back to the microservice definition, and our compiler. The NATS connection, database pool, and compiler is set up, and then we call make service. Let's dive into that. So this is now starting to use the NATS microservice framework. So we just have to go through some rigmarole here to set things up and register the service. So you create a micro config where we give the service a name, version, description, and an optional error handler. So the error handler will be called if something goes wrong with the service itself set up. So when that happens, I just want to log an error. You could do something else, send some open telemetry error information, keep things simple. I've just logged an error. Then you call micro.add service. So this is actually going to add a service into register it with NATS. Next, we're going to add a group of related endpoints. So the group means our endpoints that we add onto that group are all going to have the same prefix. So it's going to be stock.add, stock.remove, and stock.get. And then the only other things we need to do is register a handler function for each endpoint. So as we add an endpoint, the first option is the NATS subject that's going to be added on. So we've got stock.add, and then we have a handler function. So this handler function is called every time a request comes in on the subject, and it's responsible for sending a response. So all of our handler functions are wrapped inside this method called a trace handler. We'll look at that in a second. And then they have their own, the real handler under the covers that's actually going to perform, in this case, stock add. So let's scroll down and have a little look at this trace handler that wraps all of those things. So the trace handler, all its job is to do is to capture a bit of OpenTelemetry information about each API call. So all it does is it takes as its parameters a handler function itself. So it's going to wrap it. It starts a new context and gets the OpenTelemetry tracer and starts a new span. So each API call is going to be wrapped in a span as an independent kind of thing. And then it's going to call defer span.end. So when this function finishes, that span will be closed off and sent to our OpenTelemetry backend. We make an API call to log the fact that an API request is started on the subject, and then we call the handler. So the handler, in our case, will be the stock add handler. So it starts the span, calls the stock add handler, at the end it's closing off that span, and we'll get all the information about it running through. The important thing to note is we pass the context down that we create here. So that allows a bunch of information to propagate down about what spans open and so forth. So that's pretty common in Go. functions take a context as their first argument, and we're following that here. So let's dive into the stock add handler. It takes the context and it takes the raw request that were given by Nats. So I'm going to create an object called raw, and I'm using this new request scope. And this is a parameterized type, and it takes our schema's stock add request. It passes in the context, the request, the Nats connection, and our database pool. So what's a request scope? Let's have a look at that. So this function, new request scope, takes any type as a type parameter, passes, like say, those values through that we just talked about, and returns one of these request scope objects. The approach I like to take with my request handlers that are written in this Nats framework is I like to have a single structure that's created for each request. It contains all of the data we need as the request runs through, and at the end of the request we discard it. So let's have a look and see what we put on that. So as you can see, the request scope takes a type parameter of any, and we use that to hold the Go structure that represents the decoded request. So when we're calling it for an add request API endpoint, it will have the structure that's needed for the add request. If it was for the remove a stock endpoint, it would have a different structure in there. So we parameterize it because we want our code further down the track to be able to use those values in a type safe way. So inside the add handler, we want it to be able to get this decoded value as an add request object. Go is a statically typed language, so we want to use the tools and techniques so we can actually use the correct types inside our correct objects. So there's a few little tricks you have to do to get that working. What else is in the request scope? We've got our Nats connection, we've got our raw request. The next thing we hold is an error. Now when I'm running through the different processing for a request, what I do is if I get an error anywhere along the way, I'm going to populate it into this field. And that's a signal for the next steps to say, oh, well, an error's happened, so maybe I don't need to do what I normally do. For example, if an error happens while we're decoding the JSON request, maybe the caller didn't send valid JSON, then we're not going to try and attempt to update something in the database. So we'd catch that error when we're decoding the request and save it on this object. Then the next call is going to check to see if there is any error in this field here before proceeding. We'll see that as we go through. Next, we've got three fields which are related to the database connection. First of all, we've got a connection from our pool. Then we start a database transaction, so we hold that in this field. And if you recall from our database episode, whenever we're interacting with the database through SQL-C generated code, we need one of these db.queries objects. So we declare one of those here. So it's been created and is convenient to use. Decoded type, I touched on that earlier. We've called into the new request scope and we create that object, and it immediately calls setup dbcon on that new scope, passing in the context in the pool. So this function is designed to establish a database connection. See how it works. You'll notice at the top of these functions now we start to add a bunch of standard calls so that we can capture our open telemetry data. Why do we do that? As a reminder, so we can see how long the program is spending in this particular function. So They all follow a standard pattern, and I'll only explain it here and we'll skip over it next time. But we call the telemetry get tracer, and then we use that to start a new span, passing in the context and give it a name. So this is the name that you'll see over in New Relic or your OpenTelemetry provider. So it enables you to say, link this back to what part of the code is running. You always want to defer span.n. So regardless of how this function is returned, that span will be closed correctly and will look correct in the tracing. The next steps are about setting up our database objects that we need. So first of all, we're going to acquire a connection from the pool. Remember, we've got a fixed set of connections available. There are lots of requests coming in, so each one has to grab an unused connection from the pool, use it, and then return it back to the pool. So that's what this call is doing. If it doesn't work, we're going to add a system error to our request. We're going to set the span status to be error. So what's adding a system error doing? If you recall earlier, I said each request has got that error object, and calling this add system error will populate our error onto that object. It's also going to mark it as being a system error rather than a caller error. So the way that I like to design my systems is I want to distinguish between errors that I as a developer have to deal with versus errors the responsibility of the caller of the API. So let me give you an example. An error that I have to deal with is this one here. If our system is trying to get a database connection from the pool and it gets an error, that's my problem, and I have to investigate what happened there. Maybe I've run out of connections in the pool, I need to increase the size. Maybe there's some problem with the database. That's my responsibility. The end user who's called that API can't fix that problem, it's up to me. This is opposed to a caller error. So this is where the API caller makes an API call and something goes wrong, but it's their responsibility to fix it. So a good example would be they've provided invalid JSON, or the JSON might be valid, but it doesn't meet our business requirements. So what we want to indicate there is, hey, you need to go, here's the problem you need to go fix, give them that in the response, but we don't have to do, as a developer, do anything to fix that, because that's really the caller's responsibility. So system errors for developers to fix, caller errors for API callers to fix. You'll notice that whenever I create a system error, I also set the status on the span to be error. This means it's going to show up, I can be alerted on it inside my OpenTelemetry system, because those are the ones that I need to know about. So you'd have the appropriate hooks there to be notified about them, contact your team, open tickets and investigate them. All the caller errors I'm not actually interested in. I don't need to do that same thing. They're normal course of events. It's actually up to the caller to monitor and trace for those. That's just my perspective on it. Okay, let's move on. Let's assume we acquire a connection. Then we begin a transaction and we store that also on our request structure. Standard error handling, if that didn't work, it's a system error. And last but not least, we take that transaction and we create a new queries object. So now we're ready to call one of those SQL-C generated database access methods. Great. Let's go back to our new request scope, and that returns the new request scope. Go back again. Right. So we've now created our new request scope. This next line here is very interesting, because all we're doing is we're going to wrap that request scope in something called a stock add scope, which is defined up above. The whole purpose of this is a very lightweight wrapper that gives some type safety to our request. And what this means is we can use that generic sort of request object in the context of our stock add request handler, and we can get the Go object that represents the incoming request in a type-safe fashion. So if we didn't do that, we had a generic object and it just had type any, we'd have to be casting that object to our stock request object every time we wanted to use it. But you'll see below, by creating this little wrapper, we can now just get that value out and it's in the right Go type. And so Go's all about type safety. We're going to use a little trick here so we can leverage that. The following command, rs close, that's going to make sure that our request scope is closed. We're going to come back to the close command when we hit the go through the other functions. Validate JSON. So let's see what we're passing in here. Our context, our JSON schema compiler, the request.data. So this is the incoming request from Nats. The data method gives you that message just as a bunch of bytes. So Nats messages, it doesn't know about their content, it just gives you the bytes. And the last parameter is the JSON schema identifier that we want to validate those bytes against. So let's see how that works. Okay, we start off with our standard tracing. And here's the first example we've seen of where we're checking if an error has happened earlier and we bail early. So rs has error. Let's quickly dive into that. It just says, it returns if rs has an error or not. So we've got an error, we bail. Next, it checks if the JSON data, which is the bytes passed in, if that's empty, that's a caller error. So that would be the case where the caller has passed no data at all. If our compiler has been passed in nil, that's a system error. I forgot to pass that object in. Next thing we do is we compile the schema name that's passed in. If that had an error, that would be a system error. So that's my responsibility to make sure that that schema exists in the system. If the schema was returned from the compiler was nil, that would be another problem for the system to deal with. The next thing we do is we use the JSON schema unmarshal JSON method. Passing in our raw bytes, this parses those bytes into a format that the JSON schema compiler can use to perform its validation. So again, if that has a problem, that will be a caller error because it would indicate some sort of invalid JSON. So finally, we get to the crux of what this method's all about. It's actually going to perform the validation. So error equals schema.validate with that unmarshaled data. And this is where all the magic happens. The JSON schema compiler is comparing that JSON against the schema and performing validation against every single field that we configured it to do. So all the required fields, are they all in the right formats, and so on and so forth. So in this little handful of lines, that's performing all that validation for us. If it returns an error, that is straight back to the caller. Hey, the schema says this, you haven't provided it, kind of thing. Assuming we get past that, our schema and the JSON match. The next step is to decode the request. This is going to take the raw JSON and unmarshal it into our JSON structure. We've already unmarshaled it once before into the format that the JSON schema compiler used, but we can't use that here. That's a different format. We want to unmarshal it into our own structure. So let's see how that works. We have the standard tracing. Then we check for previous errors and bail if that was the case. And now we are declaring our type, which is a type parameter passed in here. So in this case, it would be the add stock request structure. we unmarshal the raw data from our message into that request. And if there's an error, again, that would be some kind of error from the caller's perspective, so we record that there. And then we just store it on the request. So this is our generic field that's going to hold our specific decoded request structure. Great, so now we've got the data out of our message and into our Go structure, ready for the rest of the application to use. Okay, what happens next? We're going to create a variable called added and set it to the rs add stock method, passing in the context. Add stock's just below. This is going to add the stock into the actual inventory in the database. Standard preamble, tracing and error handling. Okay, here's the method I sort of inferred at earlier, where we're going to get our type safe value that we're storing on our request. We just call rs.request, and it's going to return us a schema stock add request. So if we're calling the same function on another sort of request, it will return the type that's appropriate for that. So once we've got our request object, we can just call our generated code that SQL generated for us. So we db.add inventory params. We're setting up the parameters to add to our inventory. So it needs a product SKU, which we take from the request. Whoops. And a stock level. And then we call rs, our request queries object, add inventory, passing in our context and our parameters. That could either succeed or fail. If it fails, that's a system error. So there's no error condition that could be a caller perspective there. It's all a sort of a system error. And what that returns, something called a DB inventory. So that returns the newly updated rows in the database, or row I should say in the database. So we want to return that row back because we need to return that data back to the caller in the response. The next thing we want to do is commit or rollback. Let's see what that's all about. Commit or rollback is going to commit the transaction if we had no errors. Any errors, we're going to roll back the transaction. So committing the transaction means make permanent all of the database changes since we started the transaction at the top of the request. Rollback means abandon all of those changes. So if we've got some sort of problem, we don't know what the state of the system should be in, so we're going to just roll back to where we started. If everything's good, we'll commit and move forward. This function's written in quite a defensive style. So there could be errors like at lots of places in the system. We could have had an error just trying to get a database connection. We could have had an error when we're validating the JSON. We don't really know. So what we want to do is not assume too much before we try and commit or roll back. So for example, the first thing it does here is, hey, if I never got a transaction, I can't really commit or roll back. It's like I never started anything. So it's going to return straight away in that case. The next thing I do is our default message is transaction commit, but then if we had an error, so this is just if an error occurred on the request, we'll change that message to be rollback because I want to log what happened. So we're going to do our normal telemetry, and we're going to pass that message through. So if we look at the traces, we can see if it was a commit or a rollback. We're going to defer a function that's going to clean out the transaction object once we get to this point to set it to nil. If we did have an error, then this is where we do our rollback. So now we get into like a real weird case. We could have started a transaction, had an error, now we're trying to roll back, and the rollback itself gets another error. So we just want to add a system error in here. That's not a lot we can do there. It's probably a bit of a deep investigation as to what happened. If there were no errors though, and we get past this point, so there were no errors, we want to commit, and again the commit could fail, so we'd record an error at that point. So our database is now either been committed or rolled back, and the last thing for us to do from a user perspective is to give them their response. So let's see how that happens. So we call respond JSON, but we need to create the response first. So let's look and see how that works. So make stock response, we've got our standard telemetry, and then we declare a new variable that's going to contain that response. So what I'd like to do with my API responses is they're either going to kind of go down two paths. They're either going to contain an error or they're going to be okay. So I use a variable called okay, and in the happy path, that okay is going to be true, and your response is going to contain, in this case, our product SKU and quantity. On the other hand, if we encountered an error, we'll set OK to false, and then we'll provide an error string so that the caller knows what happened. If we encounter an error on this request, we're going to set OK to false and pop a pointer to the error value. This utility class just turns a string into a pointer to a string. Here's the happy path. If everything went fine, we set OK to true, and we populate the SKU and quantity, and we return that object. Okay, so this gives us a response structure, and let's see how that's returned to the caller. In the response JSON method, we pass in the context, the original request from Nats, and we've got our API response. We perform the standard telemetry, and then we're going to set up a Nats header which can be sent with our response message, and that contains the trace parent value, which allows you to look up this particular interaction inside, say, New Relic, which is the OpenTelemetry provider. So it's important to send that back to the client, so if they get an error, they could maybe quote that back to you and say, hey, I got an error on this request, can you tell me what happened? You could take that and look it up. And what we do is we're going to call respond JSON. So this is part of the framework that's provided by Nats. You pass in your response, our Go structure, and it's going to just encode it into JSON using the standard library, and we're going to pass in our headers. Something can always go wrong, so we could have all this work properly and maybe the connection to Nats is broken at this point. So if that didn't work, we're going to set our status to error and log that. So at least we'll have, hopefully in our telemetry system, a record of what happened here. That almost takes us to the end of the stock add handler, but I said I'd go back to look at this close function. So that's something that's deferred, which means it's going to run right when we return from here. And let's dive in and have a look at that. The close function is designed to clean up our resources. We've come to the end of our request. We want to tidy up and make sure this request is completely closed off. It's released any resources that are acquired along the way. So if we somehow got here with our transaction still open, we're going to just roll that back and record an error if that failed and set it to nil. I'm not even sure if this would ever really be called, but I put it in there because it's part of defensive programming. Yeah. If we still have a connection to the database that we've taken from the pool earlier, we're going to release it back to the pool. So this means we're not going to just take things out of the pool and consume all of our database connections. As each request happens, it pulls one out of the pool. At the end, we want to release it back to the pool, so it's available for the next request to use. So that kind of brings us to the end of that API handler. The other ones are pretty much similar. They follow the same patterns, so you can look at those in your own time if you can. We also haven't covered every single part of the code in the system. So if you want to look yourself, there are unit tests in the app test go package. Now these tests, when they run a real NAT server in process, and they connect to our test Postgres database. I like that approach because it means that the code being executed is really close to our production code. So these tests avoid mocking out complete layers of the system. So using a real application server and a real database. You can run the tests by running make test. I've also included a linter. So linters go a little bit further than tests, and they check things like coding style and maybe catch for things like you're opening a database connection but you forgot to release it. So they're kind of higher level sort of coding problems. So for the linter I've used, it's kind of really slow to run. I haven't investigated why that is, but it's not so much of a problem because I only run it periodically. Linters are a really valuable tool that casts an extra set of eyes over your code. One thing we always want to do with our production code is always ensure that our tests are passing. So I've included a simple GitHub action. You can open that in the .github/workflows/pr-ci.yaml. That's triggered whenever I open a pull request. So this action will check out the code, build the system, run the tests and the linters. All of this happens in the background on GitHub's infrastructure. And if any of those steps fail, then it'll prevent my PR from being merged into the main branch. It's a great way to kind of keep your code in good shape at all times. So this concludes my series on production grade systems development. We've developed an API microservice using NATs, Postgres, and OpenTelemetry, all written in the Go language. We discussed a whole bunch of different topics like development environments, testing, telemetry, performance, reliability, and a whole lot more. So I really hope that you got something out of the series, and all the best of luck and blessings for you in your software development journey. Remember, iron sharpens iron, and one man sharpens another. Thanks for watching.